the vanishing coin trick. Place a coin on the table and then put a glass beaker on top of it. You need to be looking through the side of the beaker at the coin. Then pour water quickly into the beaker and, as if by magic, the coin disappears. Here you can see a ray of light travelling through glass, and as it crosses the boundary between the glass and the air, it's refracted, which means it speeds up and so it bends away from the normal. So angle theta 1 between the ray and the normal is bigger than angle theta 2. Now we know that light is reversible, so if the light was travelling in this direction through the air and it met the boundary, it would be refracted and travel in this direction. So using Snell's law, I can say that sine of theta 1 over sine of theta 2 must equal the refractive index of glass. Now I want to think about what's going to happen to these angles when I increase angle theta 2. So as theta 2 increases, theta 1 is going to increase until we get to this situation where theta 1 has become 90 degrees. And so I'm going to call this angle here, theta 2, has become a special angle which we call the critical angle, so I'm going to call that theta c. So substituting those values into Snell's law equation here, I can say I've got sine of 90 degrees over the sine of the critical angle equals the refractive index of glass. Now we know that the sine of 90 degrees is 1, so 1 over sine theta c equals ng, or just rearrange that to get sine theta c equals 1 over the refractive index of glass. Let's now consider a more general case where we've got two transparent materials, material 1 and material 2, such that the speed of light in material 1, C1, is greater than the speed of light in material 2. Okay, that's why the light bends away from the normal when it goes from material 2 to material 1. Now this also means that the refractive index, or the absolute refractive index, N1, must be less than the absolute refractive index, N2. So, if I apply Snell's law to this, I get N from 1 to 2 equals sine theta 1 over sine theta 2, and that equals N2 over N1. Okay, so let's increase theta 2 again until we reach the critical angle. So here we are, we've now reached the critical angle, so we've got the critical angle here and the angle of refraction here is 90 degrees. So that means that theta 1 is now 90, so I've got sine of 90 degrees over sine theta c equals the refractive index from 1 to 2, which equals N2 over N1. Again, remember, sine of 90 is 1, So that's 1 over sine theta c equals n from 1 to 2, which equals the absolute refractive index n2 over n1, and I can just rearrange that to get sine theta c equals 1 over n from 1 to 2, which equals n1 over n2. So that's the general form of the equation relating the critical angle to the refractive index of the material that the light's travelling through. Here we can see a ray of light being refracted as it crosses the boundary between perspex and air. As the angle of incidence increases, we can see the angle of refraction also increasing. And here we have reached the critical angle where the angle of refraction is 90 degrees. The question is, what's going to happen if we increase the angle of incidence further? Well, here we can see with an angle of incidence greater than the critical angle, none of the light passes through the boundary between the perspex and air. It reflects off the boundary, and we call this total internal reflection. Here we can see light being refracted as it crosses the boundary between water and air. As we increase the angle of incidence, you can see that once it is greater than the critical angle, the light reflects off the boundary between the water and the air, and this is what we call total internal reflection.